Welcome to the Science Fair. I hope you enjoy all the physics, chemistry, and anatomy and physiology projects.
Introduce yourselves, tell us about your project and what you've learned from it.
Hi, I'm Gianna David. I'm a sophomore.
I'm Anushka Talukdar. I'm a sophomore.
So we were exploring the relationship between pH and how acids and bases react with each other.
So our experiment was basically to test if different concentrations of vinegar produce the same equivalence point. And this experiment's results can be used in different fields and different applications, such as like pharmaceutical stuff. And it helps determine the relationship between acids and bases. And yeah, our hypothesis was disproved, but it's okay.
We learned a lot from it. Honestly, it definitely did not go the way we thought, but further diving into the relationship and understanding things such as the collision theory and stoichiometry, we were able to learn a lot more that we could apply for our futures.
Thank you very much. I'd like you guys to introduce yourselves and talk about what your project is and what you learned from it.
Hello, my name is Quinn Palmer,
I'm Tyler Ostroff.
and we decided for our project to be, we titled it The Purity Pursuit, how many cycles to turn ocean water to fresh water. Basically, we are seeing how many desalination cycles it takes to purify water. We're also using distillation to do this as well. So,
There's a major global worldwide problem of access to water in like many places. So we were trying to test out and see how many cycles it would take to get to the limit of 250 milligrams per liter.
250 is the standard safety procedure for salt. If it goes anything over that, it is not drinkable. So our hypothesis is if ocean water is desalinated in repeated cycles, the chloride concentration will decrease significantly and reach the potable water standard in 2 cycles. So our research, we are going to be using Moore's titration method here, and it's where you get silver nitrate and you pour it into the beaker, and in the beaker we made our own salt water. We didn't get it from the ocean, so we made our own, and we added it with some potassium chromate. And what you do is you let the silver nitrate slightly drip into it, and we have this magnet spinning in it, seen in the picture. And the second it changes color, that's when you know the chloride concentration is good and you can stop. Then from there, we can go to distilling. You want to talk about distilling?
Yeah, then we distilled the water. We did 1 cycle, and after the 1 cycle, it got down to around 200 milligrams per liter, which was below the 250 milligram per liter limit. And that was definitely a lot. That was less than we thought. We thought it would take 2 cycles. It only took 1. And overall, it was a successful experiment. And our data, here's a graph here. It shows it started at 21,000 milligrams per liter of chloride concentration and got down to around 200.
And just diving into distillation, basically how it works is we start here with just some salt water, and then underneath it's a heater, and we heat it, and in this pipe there's cold water running through, and then as this heats, the gas goes through here, and it'll be gas, but since the cold water's there, it'll send it back to a liquid, and the salt will be separated from the water, and that's how you do it. And yeah, that's basically our project. It took 1 cycle, we thought it'd take 2, and I think it was a success.
All right, well, thank you very much. I'd like you to introduce yourselves, tell us about your project and what you learned from it.
Hi, I'm Kit Fallon. Hi, I'm Grace Morrison. We're both sophomores. And we did our project on how heat affects the performance of laundry detergent. And basically, our hypothesis was that the hotter the water, the more stain removal will occur, and our hypothesis was proven correct. On our poster, we hung up all of the different cloths so you can see which one worked the best. And we determined that with like a formula of lightness value, the hot and soap worked the best out of all of them. Yeah. So basically for our procedure, we took cloth from a white t-shirt and dyed it with blue food coloring and oil, specifically olive oil. We washed it with specific amounts of Tide detergent and water based on the different temperatures, and then dried them, and then after that we uploaded the photos into 8-bit or Fiji/ImageJ software and converted them into 8-bit, which then gave us the lightness value to then put it into our equation.
Yeah.
What did you guys learn from your project?
We learned that for getting rid of tough stains, hot water is the best option, and even though it is the worst for the environment, if you need to get rid of oil stains or dyes, it's the best. But for regular day-to-day washes, cold water just does as well. It can, if you use cold water, it can save you up to hundreds of dollars per year for a family.
All right, well, thank you very much. I'd like to just introduce yourselves and talk about your project and what you learned from it.
My name's Izzy, and
My name's Cam.
we did thermal shields, which we tested which materials would be best for keeping water the warmest for the longest amount of time. And we found from our experiment that paper was the best, with aluminum falling shortly behind. And
Plastic wrap came in third to last, and then the control obviously was the worst, just not having any coverage, let a lot of heat out the most. So
And our trial lasted 20 minutes, which we took data sets between each minute in those 20 minutes, and we did 4 trials as well, and that's what we found, that the paper towels actually was the best out of all of them.
And then just some like errors with our experiment was like just the starting temperature, it varied between each material. Just like as like we were pouring it in and measuring it out, it lost temperature over time. So that just kind of just influenced the results a little bit. And then also like the integrity of the seal, with air being in between each layer, just not being able to like basically letting more air out through those gaps, just it influenced our results.
And each time we did the trial, we started at the same temperature, so it would be consistent throughout, which really helped our data results as well, which was key to this experiment.
And we actually hypothesized that aluminum foil worked the best, so we were actually surprised that when the paper towels ended up being the best.
And what you guys learned from your project?
Well, we learned that paper towels ended up being the best insulator, which was shocking to me because I use aluminum foil or aluminum for most of my hot beverages, so that was really shocking. And learned how to take quantitative data as well and really focus on that.
Yeah, and also not just with liquid, but with food as well. We can use paper towels even more in our household. We always used aluminum foil, so now just learning this new data, it can apply to our lives really well.
All right, well, thank you very much.
Thank you.
Introduce yourselves, talk about your project and what you learned from it.
All right, perfect. I'm Holden Young. This is our project, Chemistry of Collision. This is my partner, Dylan Reese. Want to start us off here?
All right, so our question was to answer which ratio between sodium bicarbonate and vinegar was the most effective in creating carbon dioxide gas efficiently.
Basically, the purpose of this was to figure out what ratio of baking soda and vinegar would produce the most effective and quick reaction to fill up an airbag, because the roads on the U.S. are particularly dangerous. Yeah. Dylan, why don't you take over the next couple?
All right, our hypothesis was if the ratio between vinegar and sodium bicarbonate is 14.3 to 1, then it will result in the most effective reaction. Basically, our concept was to use a water displacement system to measure the time it took to generate 250 milliliters of gas, and use different ratios to test which took the shortest amount of time and which was most efficient.
Our variables include the independent variable was the baking soda and vinegar. The dependent variable was the time measured in the mixing of reactions to the given volume. And the constant variable was the size of the bag, 250 milliliters, and the total amount of mixture, which is 20 grams. Take it out from here. You gotta finish it up.
From our data, we concluded that our hypothesis was wrong, and actually the ratio of 6-to-1 was most effective. This could have been for multiple reasons, but mainly because we didn't consider the area of the reactants when mixing, and not our theory circled around perfect molar reaction, and we were unable to achieve that.
Perfect. Thank you.
All right, thank you very much. Introduce yourselves, talk about your project, and what you learned from it.
All right, I'm Zach Goldman,
I'm Amaya Scott.
and our project was to show how if the temperature of sunscreen will affect how effective it is to the skin and how much damage it can cause. So we found that we used 3 different temperatures of sunscreen: a hot, cold, and room temperature. And we used photochromic beads to show their UV exposure and the intensity that they brought in.
Yeah, the beads are made of like spiral compounds which release pigment when exposed to UVA light, which is how they change color as it shows there. And we used like a petri dish to like cover the beads with sunscreen at different temperatures, and we measured the amount of color change per each trial to find the average amount.
And our graphs and tables can show that for the colder trials, there were limited beads that changed color, but when you get up to the hotter trials, the majority of the beads changed color, which meant that the UV rays were able to seep into the sunscreen and affect the beads more. So at the pie charts over there, the hot was 66% change and the cold was 25%. So there was a big drop off of how effective it was.
Yeah. So our original hypothesis was that if it was stored at higher temperatures, then it would be less effective than sunscreen stored at colder temperatures, and that was proven by all of our data that Zach just talked about.
I think that's it.
What did you guys learn from your project specifically? Like any, real-world applications to this?
A lesson for sure is to store your sunscreen in cooler temperatures like a fridge, or if you go to the beach, keep it in a cooler or under a towel so the chemicals don't get deteriorated and destroyed.
I learned that, like Zach said, that I should keep my sunscreen in colder places, and I also learned a lot about the electromagnetic spectrum and how your skin can be like really irreversibly damaged by UVA rays.
All right, well, very cool project, thanks.
Thank you.
Can you introduce yourselves and talk about your project and what you learned from it?
Sure. I'm Noah Whirl. My project is a guitar pick experiment, and it is about finding whether or not different guitar picks affect a guitar differently, like tone-wise.
Can you explain more, like?
Yeah. So, after doing a little bit of experimenting, found out that like a sharper pick gives like a guitar pick something called like attack, so it's like higher frequencies, higher pitches, and whereas like a dull low pick, lower attack because it doesn't strike the string as hard. So if you're looking to change the tone of a guitar pick, I recommend, if you're looking for a higher, brighter sound, go for a sharper pick, and then like a lower, duller, warmer sound, go for a...
Can you talk more about your hypothesis and results?
Sure. So my hypothesis is if a guitarist uses a differently shaped guitar pick, then the tone of the guitar will change. And that's my hypothesis.
And did you prove it or disprove it?
Oh yeah, so the way I did this, I took this tool, which is online mic test, it's like a website, and I measured the frequency in hertz per like pick. So like, for example, pick C, which was like a Dunlop big stubby pick, it gets like a lower frequency in there, while like a pick like a Fender offset pick gets a higher frequency.
Well, thank you very much. Introduce yourself and talk about your project and what you learned.
Hi, so I'm Amelia Barreau, and this is my partner.
Anna Canders.
And so we wanted to test the effects of ocean acidification on the rate of erosion of shells. And so we found that this was very relevant in our current society because as humans are continuing to release carbon dioxide into the atmosphere, the ocean is absorbing 30% of that, and it lowers the ocean acidification, which causes a faster erosion rate of shells.
Can I just hold this? Sorry. And basically we did this using hydrochloric acid, which is an acid sorry. Basically, as oceans absorb the carbon dioxide, as Amelia said, it becomes like more acidic. So we represented that with the hydrochloric acid, and we reacted it with the shells. And basically, due to the chemical equation, basically we measured how much carbon dioxide was released, basically seeing how it displaced the water, and then we measured that every 30 seconds for 3 minutes.
So as we had suspected, we found that the lower the acidification, the faster the erosion rate of shells. So in the first 30 seconds, the lower acidity or highest intensity of hydrochloric acid produced 75 milliliters of gas in the first 30 seconds, whereas in the intermediate trial, we had 55 milliliters of gas produced in the first 30 seconds, and then the highest acidification or lowest intensity of hydrochloric acid produced on average around 15 milliliters of carbon dioxide in the first 15 seconds or 30 seconds. So yeah, so we found that this is affecting local habitats like clams, oysters, any organisms that have calcium carbonate skeleton, and we came to the understanding that as more carbon dioxide is being released, it's really harming our local habitats, and so we kind of just wanted to investigate that and raise awareness about that.
All right, well, thank you very much.
Thank you.
Please introduce yourselves and talk about your project and what you learned.
Hi, I'm Juliana.
Hi, I'm Olivia.
So our project was about the removal of microplastics with ferrofluid, so we labeled it Ferrofluid to the Rescue.
Our goal was to determine which of the three types of microplastics, HPDE, PET, and EPS, would be best removed using a oil-based ferrofluid solution from the ocean water.
So our problem is that our oceans today are filled with 75 to 199 million tons of microplastics, so we wanted to figure out a way to remove those microplastics from the ocean. So our hypothesis was if the oil-based ferrofluid can remove the microplastics, then out of the three types, HDPE, PET, and EPS, EPS will be the best removed and HDPE will be the worst removed.
Our background and research we did for the project was we first discovered the different types of makeup of the three plastics. HDPE and PET were both triple bonded plastics and they had very slick surfaces, well as EPS had a lot of pore surfaces and it was only single bonded.
And then all the microplastics and ferrofluid are hydrophobic, meaning that they repel the water instead of attract it. So because they're all hydrophobic, that is what allowed the microplastics and ferrofluid to bond together. And porosity is basically the measurement of open space or pores in a microplastic. So that's why we thought EPS would be the best remove, because it has many pores that the ferrofluid can get into and pick it up. And our hypothesis was correct, with EPS having a 94% recovery rate, which was also shown in both of our data. So for our trials, we did 50 grams of each microplastic and 2 grams of the ferrofluid. And then here, 0.47 grams of microplastics were removed for EPS and only 0.3 were left behind, unlike HDPE and PET, which left behind many more. And over here, the recovery rate for EPS was 94%, and the recovery rate for HDPE was 88, and for PET was 76. And the materials we used were the microplastics, the ferrofluid, the water, and a magnet.
We made the ferrofluid ourselves. It looks like this. It's diluted in salt water to make sure it can't stick to the glass. And with it, we mixed vegetable oil and iron oxide powder.
So our procedure was we put on gloves and all safety equipment, And then we filled each cup with 90 milliliters of water and let it sit out for 20 to 30 minutes to get to room temperature, because you cannot do it with hot water or the ferrofluid will melt. And then we poured the microplastics in and we let them sit for 2 minutes. And then we poured the ferrofluid in and we stirred it all together. And then after it was done, we measured the microplastics taken out and the ones left in, and then we cleaned up. And do you want to do the discussion?
To clean up, you have to use soap first, since it's an oil-based product, so just water won't work. And you just use it, wipe it out with paper towels, and then it will all be gone, and you just wipe it with soap after.
And then for our discussion and conclusion, our hypothesis was correct because EPS was removed the best, and the scientific reasoning for that is because EPS is removed the best because the ferrofluid can seep into the pores, and it has a very light density, which allows the ferrofluid to pick it up very easy. And that's our project.
All right, thank you guys.
Thank you.
Could you introduce yourselves and tell us about your project and what you learned?
Yeah, hi, I'm Sydney Heiskell. I did Foudy Foundations, how triglyceride composition shapes the physical properties of soap. So basically, I produced soap with different types of oils and saw how those oils affected the different physical compositions of the soaps and the physical properties of them. So the purpose is because when people are making the soaps, they need to understand what oils have what different properties in order to cater to different preferences and skin types. So it's crucial for soap making businesses to explore like all the different types. So soap itself is made by mixing a triglyceride, which is the fatty acid, or it's the fat molecule, with a base. In this case, I use lye or sodium hydroxide. And so in this process, saponification occurs, the glycerol is converted into glycerin, and then it produces the actual soap molecules. And so when the triglycerides are shorter in length, it means that they are more hydrophilic or can dissolve more and will suds up a lot more. But the longer they are, it also means that they're a lot more stable in the suds, and the suds themselves can last longer. And then if they're unsaturated, they can have kinks in their actual chain, so they can't pack as close together, so they're a lot less dense. So I ended up producing the soaps. I tested for density, suds, and the solubility of them with using tallow, olive oil, and coconut oil. Olive oil is a long chain unsaturated fatty acid. Coconut oil is a medium length saturated fatty acid, and tallow is 1/2 saturated, 1/2 unsaturated long chain and fatty acid. So my results ended up backing up my hypothesis, and everything I kind of predicted came true. Olive oil was the least dense, had the least amount of suds, was the least soluble, but also it produced the most stable suds. So if you're looking for a bar of soap that will last the longest and the suds will stay along for longer, it's kind of the ideal choice. Coconut oil had the most soluble, so it dissolved the fastest. It was the densest, but it also had the highest rate of decay. The suds did not last as long. So if you want something that's a lot sudsier, that's kind of the best. And then tallow was kind of the perfect mix of both. So if you want something more in the middle, that was kind of the middle ground there. Yeah, thank you.
Yep. Thank you very much. Could you introduce yourselves and talk about your project and what you learned from it?
My name is Janelle De La Cruz.
So my name is Thibaut.
Basically, our project is about osteoporosis. It's a disease where it affects like your bones, and like it makes them weak and brittle over time. It's due to genetics mostly, so there really is no cure. Basically, the people who get it are like mainly postmenopausal, have low body weight, who smoke a lot and don't really exercise. Here's what a normal bone looks like. The brown spots are spongy bone, and basically over time, the spongy bone gets bigger over time with osteoporosis. So yeah.
So as you can see here, the spongy bone is like a healthy, normal person here. When you get osteoporosis, the spongy bone tends to get bigger, so the bone gets weaker and it breaks easier. Yeah.
Can you talk more about like your results, hypothesis, if you proved, disproved? Could you talk more about your hypothesis or how you proved it or disproved it?
So the patients with like low bone density have higher chance to sustaining fractures, and compared to those with normal bone density. And essentially, the rationale behind the hypothesis is that bones are weak and more susceptible to break.
Basically, we just like conducted some studies, and like the fracture risk for osteoporosis for a lot of people is 24%, and some of the methods that we use were like bone mineral density screening, BMD, prospective cohort studies, case control studies, and population health databases.
All right, pretty cool. Thank you guys. Could you introduce yourselves and talk about your project and what you learned from it?
I'm Valentine Park.
Sophia Zanni.
So basically our project is about cystic fibrosis, which is a Mendelian disease, meaning that it affects one gene in your DNA. And basically it is related to an overproduction of mucus, which causes blockage in your lungs, making it very difficult to breathe, and also affects the digestive system. So for our project, we did 2 studies. My study focuses more on the chemistry of the project, focusing on the bicarbonate ions and the channels that really affect the defect within the gene. And Sophia's is more about the medication and ways to treat the disease.
So mine focus on taking 3 medications that they use on people with cystic fibrosis. So the Alexacraftor, the Tezacraftor, and the Evacraftor. And they took people the ages 12 and above. They didn't really focus too much on characteristics. They took people from all different regions with different ancestry backgrounds. They just really focused on them like having the gene. And they took it for about 20 weeks, the medication, and it really improved their quality of life and took the life expectancy from 20 to 30 years to early 50s, which is a really, really just like big improvement. And we have our model, which shows the inside of the bronchioles. So this is the one without cystic fibrosis, and this is the one with. And then we have a pair of lungs here, which you can open and show the inside, which shows the bronchioles that are most affected. And yeah. Thank you.
All right, thank you guys. Could you introduce yourself and talk about your project and what you learned?
Hi, my name is Holden Hersey, and I worked with Nora O'Reilly, who's over there explaining her own project. And my project is converting alternating current to direct current. So a little background, alternating current is what's used in buildings, in power lines, and it's used because it's very efficient at traveling long distances, and it was invented by Nikola Tesla. However, direct current, which is used in like phones and batteries and any portable devices, won't travel well in power lines, and therefore we need to convert it over from AC to DC. And we're testing the history of what is called rectification, converting AC to DC. We're testing the history and how the efficiencies changed between different ways to do so. So we have a vacuum tube, which was a very early way to do it. We have 2 diodes. These are pretty similar, just different amperage. 2 diodes, and we have what we might use in the future, like glass diodes. We have FREDs, which are fast response diodes, and we have Schottky diodes, which are just different composition. So we tested the voltage drop between them, the current drawn, and the temperature that they did. So firstly, going into temperature, after testing these for about a minute each, we found that the vacuum tube got insanely hot compared to any of these diodes, which saw no temperature change at all, almost at all. Because the vacuum tube itself needs a filament that needs to get heated up, and that filament shoots off electrons to a plate, and that's what converts the alternating current to direct current. Whereas these diodes here, they don't need any external voltage like the 5 volt that this tube requires for the filament. So it's just directly the secondaries going to them. And we found that the tube itself actually lost 60 volts from this, which is way more than any of these other solid state diodes that lost less than 1 volt each, which was pretty shocking to see how technologies change. Then we also looked at the current drawn from these, and we saw that this drew the least amount of current, the tube, which was a little unexpected, but then we looked into it and we realized that the tube itself is losing a ton of energy into heating that filament, and it's just losing those 60 volts, and that's why it's creating less current draw than these, because less current's going through it and getting to the end. So we noticed that. After the testing, we looked at these on the oscilloscope. All of the solid state diodes, so all of these guys, looked almost identical on the oscilloscope because the switching happens so fast that you can't actually see it on an oscilloscope. But what we did see is the more jagged waveform. So you see how sharp those edges are compared to the tube, which is more rounded and smooth, slower transition, which was really cool to see. And, so this here, even though it has a waveform, it's actually direct current because it's unfiltered from these. Well, it's not fully unfiltered. We have two filtering capacitors here, but they're not fully filtering it. We're still leaving a little bit of what's called ripple in it, so we can actually see the waveform itself and see what these, just them, do. So we originally had a switch, but we didn't end up using that, and we just had these leads, and then we'd screw them in 2 at a time. So each test has 2 diodes. They're 2 phases of the alternating current coming from the transformer. So we test 2 at a time, 2, 2, 2, 2, and then the 2 phases go here. So starting here, the wall power is going to come in from here, and it's going to go through the fuse and through the switch. We put a fuse there because we did blow it a couple times, learning what went wrong, what do we need to fix, and it's going to go to this transformer, which is going to step up the voltage to around 400 volts per phase. So after that, it's also going to split off to a couple other windings, like the 6.3 volts, which is commonly used for preamp tubes, but we used it for the light. And this 5 volt is going to be used to heat the heater on the tube. But the secondary, which is what comes after, the 400, around 400 per phase, around 800 together, is going to go off to each of the diodes. And then it's going to go through these capacitors to filter it a little bit. And then it's going to go to this resistor, which is going to simulate a load. It gets really, really hot. It's a 50-watt resistor. And it's going to simulate a load, and it's going to draw some current. And then that's going to go back, to ground. To ground, we have this 1 ohm resistor. And what this is doing is this is making it very easy for us to calculate the current, because using the V equals IR formula, voltage equals current times resistance, we can just do voltage times current, or voltage equals current times resistance, which is 1 ohm, so voltage equals current. So we can find that super easily. And that was the best way for us to do that. Here we have test nodes, so we can safely test all of our things, like efficiency and the voltage. And we have a ground back here to ground everything. All right.
All right, well, thank you very much. Introduce yourself and talk about your project and what you learned.
My name is Rafa, and I'm a junior. For my project, I did astrophysics, which is like I did a project where like I'm measuring the moon's brightness, like the moon like when the moon orbits around the Earth. There's like we always see like different areas of the moon, like full moon, third moon, like third moon's here, full moon's there, new moon's there. So my theory was full moon should have the most brightness and new moon should have the least brightness. Because full moon we can see the most moon illuminated on the sky. New moon is just like dark, you can't see anything there. So in order to do that, we use the photometer, which is this thing. It's a photometer. Right here. It's a photometer where we measure the moon's brightness. There is like a light sensor, which is like right here. And it connects with the laptop, and from the laptop, we can see like how much the moon's brightness is. Normally the measuring unit for light is called lux, and for a full moon, from our data we got for full moon it's like 0.83, 0.91, 1.55 lux. These are like the full moon. New moon we got like 0.01, 0.02, somewhere around there. in order to do that, we use the brightness code, which is like right there. And we like kind of command the photometer to like do it. Kind of like command like capture this light and turn it into brightness. From our graph, the tallest line is the full moon, and the line that you can't see is the new moon because it's so low you can't even see that. Some possible errors we might have, like clouds in front of the moon, and like light pollution, probably just those. And for procedure, it was very simple. Because like we like use the photometer, point the light sensor towards the moon, and like plug the photometer with the laptop and open the app called Arduino app where we can see how much light we are getting there. The purpose of this project is pretty simple, like to see like learn how like brightness affects the different like how like different phases of the moon affects its brightness, and see how brightness works, what it's like. And that's it.
Well, I'm actually a current computer science student at Wentworth, and I think it's really cool that you use code for your. So I just wanted to point that out. But otherwise, thank you very much.